Question number 11 asks you to draw the mechanism of Rubisco reacting with CO2. All right, now the way we're going to do this is we're going to try to, regardless of if we're reacting with CO2 or oxygen, we're going to start off the same way. And we're going to try to generate an enediol species between these two carbons here. Now, another thing to keep in mind is, this is a structure you do need to know, ribulose bisphosphate. And we are going to be generating, two molecules that are identical. So we need to have these phosphates at either end here. I'm trying to say, yeah. So basically, maybe that'll help you somewhat with this. And we're basically going to be cleaving. We're going to be adding on our CO2 and cleaving the top two carbons off. Maybe that can kind of help you remember where that the ketone here is on carbon 2. I don't know. Anyway, so let's get started with the mechanism. So we're going to have a base here. All right, deprotonate here, which allows now these electrons. Sorry. My bad. Getting ahead of myself in the mechanism. All right, so we're going to remember that protons next to ketones are acidic. So basically we can deprotonate here, and this is where we're going to get our enediol. Sorry, my bad. Like this. All right, so what we have then is this sort of a species. I'll just draw R for the rest of it. All right, now this enediol species here is what's going to do our nucleophilic attack on CO2. All right, to give us a carboxylic acid. All right, this should be a linear molecule. Let me just do that. All right, so now in order to do this, we're going to have the alkene electrons actually attack CO2, which means we need to basically give them a reason to leave here. Now the way we're going to do this is we want to start turning the remaining 3 carbons on the bottom into, we want to start turning this carbon, the top one, into a carboxylic acid. So we're going to base deprotonate here, which allows these electrons to collapse down, forming a ketone type species, or we're getting there, forming a CO double bond. And that frees up these alkene electrons to do a nucleophilic attack here on CO2 like so. All right, and so the end result now is we have this sort of a species. All right, so now at this stage we are ready to cleave our molecule in half. All right, and the way we're going to do that is we again want to turn, so we want each molecule to be identical. All right, the top one already has a carboxylic acid on it. All right, and so we need to turn this ketone right here into a carboxylic acid. And we're going to do this by cleaving with water. So we're going to base deprotonate. Water turning into a better nucleophile. It can do a nucleophilic attack here. All right, and initially the electrons would be pushed up onto that oxygen. Then in a second step, I'll just draw these together, right, for the sake of time here. They would collapse down and we would kick off the top portion of the molecule here. What do we have now at this stage? Well, we've got the top portion of our molecule is a carbanion. And this carbanion is somewhat stabilized by resonance. It's not a very good resonance structure, but there is some resonance stabilization to it. And the bottom portion is now this. All right. So the only thing we have to do to the top portion to make it identical is simply take the carbanion and protonate it. And voila, we've now generated 2 molecules of 3-phosphoglycerate. All right, now the question also asks how draw this reaction again with it reacting with oxygen instead of CO2. So we're going to start off in the same way. All right, so we're going to start off having by doing our creating the enediol type species here. All right, and then we're going to try to do the nucleophilic attack using the alkene electrons, but this time on a molecule of O2. Right, and when we do this, what we end up generating now is something a little different. So we can do the electron arrow pushing like that in the first 2 steps. These later things I have to erase now. Because we have something different here. All right, well, what do we have? What we have here is we have a peroxide species. All right, now this peroxide is again going to be attacked by water. Or sorry, the carbonyl down here. So the enzyme is going to do the same thing it's been doing. The only difference is that it reacted with oxygen instead of CO2. So a base can come along and deprotonate the water. The hydroxide then can do the nucleophilic attack. All right, and the electrons can then be pushed up onto the oxygen. All right, then in a second step, the electrons can collapse down, right? And when they collapse down now, in this case, we actually have kind of a good leaving group up here because of this peroxide. So these electrons from here, instead of staying as a carbanion, can come here forming a carbon and oxygen double bond, but then this oxygen here has too many bonds to it. So it can just lose a bond and lose a hydroxide on there. So the top portion becomes 2-phosphoglycolate. This molecule, and the bottom portion will be the 3-phosphoglycerate that we normally have. But dealing with this 2-phosphoglycolate has we covered it in the process of photorespiration is going to basically cost the plant energy. And that is it for this question number 11.